Hi, I'm Dmitri Melikyan. I'm the founder and CEO at Graphsignal, where we specialize on operational model monitoring. I'm going to give you an overview of machine learning model monitoring in the context of production applications. I'll be focusing on data issues as a new type of failure mode that SREs and operation teams need to consider as models are being deployed to production increasingly more often. So let's start from model serving. Just a short intro for those who are new to machine learning. A machine learning model can be trained manually or automatically, producing a model artifact in various formats. When doing inference, when the model runs, for example, it takes input data as image and outputs a classification score. So model serving is usually implemented as a web server, which exposes a REST API for model inference. Typically, it loads and runs the model file using the same machine learning library the model was trained with, for example, TensorFlow or PyTorch. Models can be served by web servers, for instance, Python, Flask, or Fast API, or specialized model servers, such as those in cloud platforms from Google, AWS. There are also on-prem versions like KF Serving. Other than providing APIs, models can just run against batches of data in streaming pipelines or scheduled jobs. So the model receives input data from other parts applications. For example, from a microservice, third-party API, or a user input. Also, other parts of the application can rely on model output. Due to this bidirectional service and data dependency, model serving needs to be a part of an overall application observability strategy. Now, here's the problem. Unlike traditional web applications, the model is fully data-driven. It's trained, it's not coded. So the data output is fully dependent on input data. This is also the case with non-ML applications, but to a much lesser extent. This means that even if there are issues with input data, the model may still run predictions without throwing an exception. Even if data is properly validated for unexpected values, things like data drift or concept drift may cause the model to output garbage that we treated normal by the rest of the application. This is well-known garbage in, garbage out problem. To illustrate this, imagine one of the features can be 0 from time to time during normal operation. But due to an error in an upstream API, all data instances have 0 for that feature. So this case is not detectable by a simple data validation script. Another example, a third-party service API has been updated, changing the data format of a returned data field. The value may still be passing validation scripts, but the model may start predicting a different class. Such problems may be detectable looking at the long-term anomalies and analyzing input feature distributions. So such silent failures are hard to detect in real life when we usually don't have ground truth to compare model outputs with. So we don't know if model predictions make any sense or not unless we monitor data for anomalies and various types of drift. Now let's look closer at data dependencies that may affect data quality. Here, there are two main risks to consider. First are the changes in upstream data dependencies. This could be a release of a microservice and an entire application. A change in data format may not be coordinated with ML team, and the model will start receiving unexpected data. Second are the bugs in upstream dependencies, resulting in missing features, for instance, nulls or zeros. Model deployment is another dimension to consider. Usually, model deployment is subject to model training process rather than application release cycle. This may mean that a new version of a model may be deployed without going through integration cycle, integration testing. This is a common problem because models are trained and validated on thoroughly prepared and cleaned up training data, not on unseen production data. Even the feature engineering code can differ from training to deployed model. In other words, a release of a model may cause model to fail on production data and needs to be closely monitored. Okay, now let's start talking about monitoring. So in machine learning, the term monitoring is used not only for monitoring in the sense of ensuring system performance and availability, but also for detecting model staleness, bias, and fairness. As far as the latter case is concerned, data scientists and machine learning engineers need to log all predictions, collect ground truth, analyze model performance by measuring feature importance, model accuracy, and so on. Those analytical jobs are rather use case specific and require custom pipelines or notebooks if it's done locally. Automation is possible, of course, but later when things get stable. On the other hand, when looking at the operational issues rather than model-specific validation and improvements, the monitoring function is optimized for low MTTR. For this purpose, continuous monitoring and detection is preferred, just like it's done in traditional application infrastructure monitoring. So here's a simple diagram to illustrate high-level reference kind of architecture for an operational monitoring system. Basically, the logger runs inside of the application, computes prediction data statistics and sends them to the server for visualizing and issue detections. In some situation, it might not be possible to integrate the logger into a model server. In those cases, the logger could monitor API requests and response to the model in the downstream service. Proper data windowing is important when logging predictions, as the statistics are computed based on time windows and not single prediction instances. In terms of technical requirements, the logger should be able to handle high number of predictions with low CPU and memory overhead. So to make sure the computed statistics have low error rates and small size, data sketching algorithms can be used. Otherwise, sending all predictions for processing would be necessary, and that would require setting up a separate data processing pipeline just for the purpose of model monitoring. One more thing to keep in mind is that pre-computation of statistics when logging needs to be data aware. For example, support text or images. While it's more or less clear what to monitor in tabular data, extracting statistics for text, images, sounds, and videos may be application dependent. In one case, the number of words in an input text may be an important metric, in other case not. It might also be helpful to log model metadata or other model and system attributes to simplify further analysis and troubleshooting. It could become useful to pinpoint the differences between A/B tested models or subsequent model versions. And to complete the monitoring system, of course, the statistics should be visualized for troubleshooting or proactive data analysis and undergo automatic issue detection. When analyzing data statistics for a running system, visualizing time series is essential to notice any changes. Just seeing summaries for a selected period of time is not very useful. One important requirement for such a dashboard is the ability to analyze feature distributions and see how they change over time. Statistical distribution distance metrics such as Earth mover's distance will help to detect as well as visually track distribution changes. But I'll not be covering data analysis and drift detection methods, which is a big topic by itself. Automatic issue detection is critical because there are usually too many input features and properties to be monitored. It's hard to manually set up alerts for each, and there is a risk of missing things. Detection is done on prediction time windows. This can range from short-term anomalies to long-term distribution changes, such as seasonal data drift. It is out of scope of traditional alerting systems to set up alerting based on complex statistical computations and custom baselining. So there are three main takeaways from this summary. Data issues in model serving is a new failure mode for machine learning engineers and MLOps teams to prepare for in order to reduce MTTR and meet SLOs. Traditional monitoring systems do not address the data quality aspects, and therefore the visibility into model serving operation will be limited. And finally, model inputs and outputs both should be monitored. Depending on the application, the implementation can range from simple checks to machine learning specific monitoring tools. Yeah, so this was a short overview of model monitoring. Feel free to contact me if you have any questions or comments. Thank you.